Hey everyone, and welcome to this module on Introduction to Continuum Mechanics, Tensor and Analysis. Uh, so for today, we have a discussion on three important topics which are quite useful in the subsequent chapters. We have this concept of the symmetric and anti-symmetric or asymmetric tensor, and we introduced the dual vector, which is quite a new concept. You haven't faced this concept yet, and it is of course available in an anti-symmetric tensor. And we have the concept of the eigenvalues and eigenvectors, which you may recall from your linear algebra. But here we're going to apply them to a tensor, but it is quite similar to the matrices. All right, let's get started by the symmetric tensor. So we define a symmetric tensor where T is equal to T transpose. So if the transpose of a tensor is equal to itself, we call it a symmetric tensor. So if I write this in this is in the tensorial notation, but in initial notation we have Tij is equal to Tji. So for example, we have T12 is equal to T21, for example. T11 is equal to T11, T32 is equal to T23, and this goes so on and so forth. Then we have the concept of anti-symmetric tensor. And we define it when T, we have a tensor T, so it is equal to the minus of its transpose. And if we write it in initial notation, we have Tij is equal to minus Tji. So for example, we have T12 equal to minus T21. T32 is equal to minus T23. And here T11 is not equal to minus T11, something like this. So if we take these two to one side, it is T11 plus T11 is equal to 0, right? So 2T11 is equal to 0. Therefore, T11 is equal to 0. And this justifies T11 is equal to T22 is equal to T33 is equal to 0. All right. So it can be proved that any tensor can be written as the sum of symmetric and anti-symmetric part. So any tensor like T can be written as the sum of its, let's say, as the sum of its symmetric and anti-symmetric part. So to give you an idea about this, we have this, let's say, T. So maybe read it here. So T can be written as the symmetric part. So I use the superscript S plus TA for the antisymmetric part, superscript A. And we have S, superscript S for the symmetric part, and we have A for the antisymmetric part. So it can be written like this, where T symmetric is nothing but T plus T transpose divided by 2, and T antisymmetric is T minus T transpose divided by 2, right? And there are quite some important properties about the trace of the symmetric and antisymmetric part of a tensor. So I would like to mention them here. So maybe some important properties you have to keep in mind. They are quite useful in the next chapter, where we consider the kinematic of a continuum. So you will see their applications in real life, but for now, if we have the trace of let's say a symmetric part, the symmetric part of a tensor times its antisymmetric, or a symmetric and an antisymmetric tensor, the trace is equal to 0. It can be proved. So to prove is like this. So if we have the trace of T, so we know that TS, TA is equal to the trace of Tij, Tji, where this shows the symmetric part, while this is the antisymmetric or asymmetric part. So according to the properties we wrote here, 1 and 2, you can write Tij as Tji and Tij as minus Tji. But for this case, we have Tji for the asymmetric part, which is equal to minus Tij. It's here. So using 1 and 2, we have the trace of, let's say, Tij can be written as Tji because it's a asymmetric part. So this is minus Tij. So we can take out the minus sign. So we have the trace of Tji, Tij, which is equal to minus trace of Tjj. And here can also be written as Tii. The left-hand side can be written as trace of Tii. Here, I mean. So we have the trace of Tii is equal to minus the trace of Tjj. And you know that J here is a dummy index, so it's just a placeholder. You can replace it with I. So this becomes the trace of Tii is equal to minus the trace of Tii. So if we take everything to one side, so it becomes 2 Tii, 2 trace of Tii is equal to 0. Therefore, trace Tii is 0. Another important property, so maybe we call this 1. is that the trace of two tensors like A and B is equal to the trace of the symmetric part plus the trace of the antisymmetric part. The third property is that I guess if you have a tensor like T and it's an anti-symmetric tensor, so the transpose of it is equal to minus TA transpose. And that's it. All right, so let's get to the next topic, which is the dual vector, and it's of course available in an anti-symmetric tensor. So the symmetric part, the symmetric tensors, they don't have a dual vector. So it's the dual vector of an anti-symmetric tensor. All right, so the idea comes from, the component of, let's say, for an anti-symmetric tensor, we have T equal to minus T transpose, right? Or in initial notation, Tij is equal to minus Tji. So the idea actually comes from here, that if you have an anti-symmetric tensor, so you know that the diagonals are 0, you have T12, T13, T23, T1, T to, oh sorry, this is 3, 1, and this is 3, 2. So if this is an anti-symmetric tensor, so maybe just write it like this. So it is minus T 1, 2, minus T 1, 3. This is minus T 2, 3. So you see here that these three components actually are here, and the rest are 0. So you can say that only 3 components are required to characterize this tensor T, or this, let's say, anti-symmetric tensor. Is quite important to be anti-symmetric. So the definition says that of a dual vector. So suppose that you have a vector like A and you want to transform it using a tensor TA, which is an anti-symmetric tensor. So you can do this simply by defining a dual vector like TA, the anti-symmetric, cross A. And I drop this here just for the sake of consistency with the book. So it says that if you have an anti-symmetric tensor and you use this to transform vector A into another vector, so you will need the cross product of the dual vector part of your tensor and A. But let's look at the components of this dual vector. All right, so let's start, for example, by writing the component of T. Here I start with T12. So it is E1 dot T A2. and I substitute this from here. So it is E1 dot, instead of T, FTA cross E2. And if you recall from, from earlier videos, we already mentioned that, so maybe from module 112, you may recall that we had A dot B cross C is equal to, so we shift one to left for one place. So we have C cross A is equal to, then we shift this, so C dot A cross B. So you can write T12 here, or maybe we can just, maybe T12 is equal to E1 dot TA E2. And I call this, let's say, star here. So if this is A dot B cross C, so you can shift this to TA dot E2 cross E1. And we know that this is nothing but minus E3, because if you have E1, 2, 3, we are moving in this direction. The, let's say, counterclockwise direction, so it is minus 3. So this is minus E3, so minus TA E3. Right, so this is the third component of the dual vector. So let's get to T13 or 31, it doesn't differ. So 13 is, 31 is equal to E3 dot TA cross E1 is equal to, again, we use this start here. We have TA dot E1 cross E3. So it is minus TA. So this is 1, 2, 3. So this 3, 1. So this becomes again minus. And it is E2. This is minus E2. I did not write 313 because it will yield into a positive value of E2. But I wanted to get all negative. I will show you why. So I have then T23 is E2 dot TA, let's say E3. So from star, we can write TA dot E2 cross E3. So it is 1, 2, and then 3. So it is, so it is 3. This is E2. So this is minus E1, minus TA E1. All right, and maybe not this one, but I would like to shift maybe all of these here a bit. So I can write E1 dot E3 dot TE1, and this is E2 dot TE3. Perfect. So as you see here, we have the first, second, and the third component of our diagonal of our dual vector. So TA can be written as minus, I factor out this minus sign here, minus of So you see that for the first one, we have T23, T23, E1 here. For E2, we have T31 plus T31, E2 plus, and this is for the third component, we have T12. This is T12, E3. And if we do the same for T21, for example, 1, 3, and 3, 2, we get positive values here. And you know that these are, they differ in a minus sign. So this is equal to T32 E1 plus T13 E2 plus T21 E3. And so if we want to find an expression in initial notation for TA, we would say that as you see here, we have T, so I, J, K. So every time you see that these are not repeated, so we have, so for example, if we have JK here, so we have I here, so it is 1, this is 2, and this is 3, so they're all, for index. And to get this minus or positive, we use the permutation symbol, so epsilon I, J, K. So this is this is positive always, but we want it to also yield negative values, so we put a negative sign here. And if you see here, I can just sum these two together, and since one is equal to the other in the value, so this becomes 2. So we have 2 of, so we have to divide this, sorry. So we have to divide this by half. So I also move this minus sign here. But basically it is written as 2TA is equal to minus epsilon ijk tjk ei. Yes, and that's it, right? Yeah. So there is an important topic here, which I would like to mention, and it is this, let's say, short explanation, where it says that if we already saw a rotation tensor. We saw that a rotation tensor, for example, its determinant is +1, so it is +1, and it is used to rotate a vector. So the axis of rotation is basically parallel to the dual vector of the rotation tensor. Let me write it and I will clarify. So yeah, axis of rotation of a rotation matrix is basically parallel to the dual vector of the rotation tensor. Actually, this becomes clear in the next chapter, where we have the del u, which is the deformation gradient. So I use the del operator here. So let's just skip it, but I just want to clarify a bit. So this deformation gradient tensor, which is a tensor, of course, a second order tensor, it has two parts. It has infinitesimal deformation or strain tensor, and it has an infinitesimal rotation tensor. So this is infinitesimal, the infinitesimal strain tensor. And this is basically the infinitesimal rotation tensor. So it says that if you want to find the transformation of, let's say, a vector like dx, which is the direction vector, so you don't need to do this, this multiplication. You just need to find the dual vector of of omega here, and you cross it with dx. This is capital X, and this is the cross product. So this is the cross product. This is the direction vector, for example. This is the dual vector of rotation of the infinitesimal tensor, capital omega. So it only states that if you have an antisymmetric tensor, like the infinitesimal rotation tensor, this is the gradient. This is the deformation gradient. All right. So basically it says that if you have the deformation gradient here, it can be written as the sum of the infinitesimal strain tensor and the infinitesimal rotation tensor. This is the symmetric part, and this is this anti-symmetric part. And here you can write this infinitesimal rotation tensor times dx, which is the direction vector. You can use simply the dual vector of omega, capital Omega, cross product of d capital X, and that's it. And let us prove it. And this is basically given in example 221.2 of the book. So it says that suppose R is a rotation tensor. And M basically is a univector in the direction of axis of rotation. So we would like to prove Q, which is the dual vector of R, is parallel to M. So that means that, for example, or in other words, Q cross M is equal to 0, because you know that this is Q and their sign, and if they are parallel to each other, so this becomes 0, and the overall expression becomes 0. So to do so, we write something like this. So if we have R, the rotation tensor, and M is a univector in the direction, therefore Rm is equal to M, because you know that this is R, the Rm, and its determinant is 1, so it finally gives 1, and M is also a unit vector. So if I multiply both sides by R transpose, you know that a rotation matrix, R transpose R, M is equal to R transpose M. So since R is a rotation tensor, R is a rotation tensor. Therefore, R transpose R is equal to R transpose is equal to the identity tensor. Therefore, you have I M is equal to R transpose M. Therefore, M is equal to R transpose M. So here we call this 2. We have this as 1. So from 1 and 2, so we have Rm is equal to M, and here we have R transpose M is equal to M. So we can sum both sides of these equalities. So M is equal to R M. Oh, sorry. If we subtract both sides, so we get R M minus R transpose M is equal to 0. So we can write this as, we can factor out M. So it is R minus R transpose is equal to 0. And R minus R transpose, if you remember from here, where we stated that it is basically here. So it is R minus R transpose. So it is equal to 2R antisymmetric. So R antisymmetric is equal to R minus R transpose divided by 2. Therefore, M 2M R 2R A M is equal to 0. And our antisymmetric dual vector is Q. So we have 2QM is 0, and we have QM is equal to 0. Oh, sorry. This is Q. So 2R antisymmetric M is equal to, let's say, 2Q cross M is equal to 0. Therefore, Q cross M is equal to 0. So it shows that the cross product of two vectors, Q, which is the dual vector, of the antisymmetric part of the rotation tensor, and M, which is a univector in the direction of, let's say, R in the direction of the rotation tensor, their cross product is 0. So it implies that they are in the same direction. Now let's get to the next topic, which is the eigenvalues and eigenvectors of a tensor. You came across this topic in algebra, in matrices, and here the concept is more or less the same. So suppose you have a vector like A and you transform it via tensor T. So the transformed vector can be written as lambda A, which is the product of the eigenvalues, and here you have your eigenvectors. So the whole idea is that if you have a vector A and you use the transformation T, then you can transform the whole the vector A into a expression into lambda A, which is parallel to A itself. And it can be proved that any vector parallel to A has the same eigenvalues, and it will give eigenvectors which are parallel to A. So for example, if you say that you have like alpha A, which is a vector, so you can take out alpha. Alpha is a scalar. So according to above, you can write this as alpha lambda A, and you can take alpha into here, A. So you can see that any vector which is parallel to A can be transformed into another vector which is parallel to the initial vector with the same eigenvalues, and it has the same, let's say, eigenvectors. Also, if we take the identity matrix for the identity matrix, the identity tensor I. So if you have I times a vector, like let's say A is equal to A, we know this. But something, let's say, in other words, this is the same as IA is equal to 1A. So 1 here is the eigen value and A is the eigenvector. So basically you can say that for any so you can say that for the identity matrix there exists infinite number of let's say eigenvectors, because you can write this as I alpha equal to 1 alpha A. Or in other words, if you have an if you have any vector, then any vector that you have here is an eigenvector for the identity tensor. That's it. Right. Okay, so now we need to find an approach to calculate how to find, let's say, eigenvalues. So in order to find eigenvalues, we use the same definition here. So we have TA equal to lambda A, and we assume that A is a unit vector. Let's say vector, I use this arrow here. So A is a unit vector. All right. And here we know that, so A dot A is 1, right? So it has a unit, it is a unit vector. So we can use this kind of notation here. So we replace A on the right-hand side with IA, because I would like to just factor out A. So if I do this, so I get TA is equal to lambda IA. So I will be able to take everything to one side of the equation, TA minus lambda IA, and I can factor out using the factorization. I can take out A. So this is T lambda I is equal to 0. So for non-trivial solution, the determinant of T minus lambda I should be equal to 0. And basically this determinant gives us the lambda. So if I write it here, I have T, okay, 1, 1, T 1, 2, T 1, 3, T 2, 1. Oh, sorry, this is minus lambda. T2, 2 minus lambda. T2, 3. This is T3, 1, 3, 2, and this is T3, 3 minus lambda. And this determinant, the determinant is called the characteristic equation. Determinant gives us an equation which is called the characteristic equation. Characteristic equation. All right. So then you can extract the lambda values. And here, how to find eigenvectors. All right. So again, we use the same equation here. So TA is equal to lambda A, then substitute, or let's replace A with IA. So TA minus lambda IA is 0, therefore AT minus lambda I is 0. And in initial notation, we have, let's say, since this is a tensor and this is a vector, so I write it like, so I transform this. I better like this as T minus lambda I, A is equal to 0. Therefore, I have T I J minus lambda. I is, you can write it like this. You have the components of it, the identity tensor. So this is delta ij, and I write here aj here. is equal to 0. And this a, I can replace it with, a alpha j, a j, because we assumed, or maybe it's better to write it a, let us assume, or let a be a I e I. So this becomes Tij minus lambda delta I j a I e I is equal to 0. So we continue with this, and I will show you what is the problem with this kind of notation here, and we correct it. Wait. Is this correct? So let's try this. Let's basically write it in a tensor. So we put 1, I1, and J1 minus lambda. I and J are equal to 1, so we have lambda. And then we have, let's say, let's write it as alpha I, because I don't want to because I can't write a as default, so I just substituted with alpha as the book also did. So I have alpha and 1, so no problem. So then I have t, so I have to sum over the, let's say, the dummy indexes here, which is I. So I can get rid of this ei as well. So this becomes so if I is 1, so I have to sum over it. So this is 2. 2, 1 minus. So you can't write this alpha here. So sorry, you can't write this lambda here because now I is 2 and j is 1. So this is 0. So we have alpha is 2 plus we have I is 3, 1, 3 minus, so lambda, then we have I3, 1, delta 1, 3 is 0. So lambda becomes 0. So lambda times 0 is 0. So we have alpha 3, which is equal to 0. But let us have a look here at this expression. We already mentioned that if we have a, a kind of vector times tensor, we follow this kind of, filling by column rather than by rows here, because this is the notation that the book came up with and we would like to follow it all through the book. Therefore, this is incorrect for the book. So we need to just change this. Let me write. But this is incorrect because we agreed to fill in the tensors by column. Therefore, the correct notation, the correct visual notation, the correct one is Tij minus lambda delta ij alpha j is equal to 0. So if we follow this kind of notation, so we have t, we sum on the, let's say on the dummy index here. So we have I as 1 always. So I is 1, 1 minus lambda is lambda times delta ij, which is 1, 1. So it becomes 1 minus delta alpha 1 plus ti is 1. So j goes to 2 minus this becomes 0. This becomes 0. Nothing here. And alpha is now 2 plus. Then we have t 1, 3. And delta 1, 3 is 0. So this is 0. So we have alpha 3 is equal to 0. So now you see that we are filling by column like this. We are filling by column. Then we have t 2, 1 alpha 1 plus t 2, 2 minus lambda alpha 2 plus t 2, 3 alpha 3 is equal to 0. Then we have t 3, 1 alpha 1 plus t 3, 2 alpha 2 plus t 3, 3 minus lambda alpha 3 is equal to 0. And from here you have 3 unknown, alpha 1, alpha 2, alpha 3, which are basically the component of your A vector, which is your eigenvector. And you have 3 equations and 3 unknown. So you solve for them and you get the answer. And you have to remember, since A is a unit vector, thus the cosine, if you have a vector e1, e2, e3, this vector here, let's say A, which creates an angle with e1, for example, theta, with e2 is gamma, and here with e3 is beta. So the cosine squares here, cosine squared theta plus cosine squared gamma plus cosine squared beta should be equal to 0, which means alpha 1 squared plus alpha 2 squared plus alpha 3 squared should be 1. So you have to bear in mind that your alpha should also, the components of your, let's say, eigenvector should also meet these restrictions here. So I thought that maybe for this part, just a demonstration could really help. So for this purpose, I used the Jupyter Notebook and the SymPy, which is a symbolic package written in Python for the symbolic calculation. And I also use LaTeX, it's a markdown language. So it gives us the, very nice outputs. So make sure you install it, otherwise you don't get the output you see here in this demonstration. So I import SymPy as SP, or you can import SymPy, so you can simply write something like, if you don't want to write SymPy SP every time, so you can say that from SymPy import everything, and you, instead of everything, you put a star sign here. So from SymPy import everything, something like this. So you don't need to write SymPy SP every time. All right, so and I have this initial and I initialize printing here. So we start with the example 222.1 in book, which is basically this tensor here. And here I use the matrix because you know, the algebra is more or less the same, but remember, this is the tensor that we had and it is written in a matrix form. So this is not a matrix at all. T is not a matrix. T is a tensor here, but I had to use this you know, tool here to create this tensor, the tensor in this example. So be careful about this. Then we have the characteristic equation, which is t minus lambda I, and the determinant should go to 0. So we said that this determinant is called the characteristic equation, and if you want to find it, we have to write some codes here. So for the characteristic equations, you need to define this lambda here for beforehand, and you need to solve for it finally to get the eigenvalues. So I simply write lambda, but as you see here, lambda turns into green kind of expression. It's a reserved word in Python, so instead I prefer to use beta. So sp dot sim and so I define beta as a symbol here, and then I have my characteristic equation here. So this characteristic equation can be found using t dot char poly, which is the characteristic polynomial equation here of beta, of course, where we defined it. And if we type in cheqn, so you'll see the characteristic equation. There it goes. This is your characteristic equation. But this is not the way that we want it. We want to solve it and we want to know the roots. So that's why I actually write simpy dot, I factor everything here in the characteristic equation, and I write it as an expression. So as xpr, if I'm not mistaken, let's see what it gets. Great. So you see that it factor out the characteristic equation here, and it shows that the root is 2. So if we calculate this using the eigenvalue value method defined in the symbolic in the simpy package, so you'll see that we have 2 3 times repeated, and this is nothing but we have 3 eigenvalues. So this is the number of the eigenvalues here, and they are equal to each other. So we have 3 values for the eigenvalue, and their value is 2. So you can use the eigenvectors to just solve for the eigenvectors. So you have 2 as the eigenvalue, and you have 3 of them, and you obviously have 3 vectors. So you have 1, 2, 3 eigenvectors here. So we go to the next example, which is 222.2. Here we have another expression here, another tensor here, 2, 2, 3 on the diagonal, and the off diagonals are 0. So when you come to such tensors, you know that you have 2 eigenvalues with 2 values and 1 with 3 value. And here I can copy this expression from here and just execute it.
So this is our characteristic equation. So you have two beta and one two values and one 3, and we can also run expressions for the eigenvalues and the eigenvectors. So you see here you have two values and one 3 value. So for the two values of 2, we have two eigenvectors, and for 3, for lambda equal to 3, we have one vector, which is here. So in the last example, 223, we have another vector here, which is like this. So it is somehow, let's say, symmetric. So one of them would be 2 because, you know, these rows and this row and this column are 0. The off diagonals are 0, but here you have to calculate everything. So we don't have any kind of idea, but we know that one of the eigenvalues is 2. So obviously one of them is 2. The other one is 5, and the other one is -5. So we have 3 let's say different eigenvalues, -5, 2, and 5, where everyone occurred once, and we have the eigenvectors here. So for -5 we have this eigenvector, for 2 we have this eigenvector, and for 5 we have this eigenvector. So if you have noticed here, all in all the tensors we discussed up until now, you can see that their values are real and symmetric. So all the eigenvectors, all the eigenvalues are also real. But if a tensor is real but not symmetric, like this one, the one from example 222, 5 here, you can see that it is not symmetric. So it may give some complex eigenvalues. So if we write the characteristic equation for this tensor here, you'll see that beta squared plus 1, this expression here, actually gives complex roots. So one of the, let's say, eigenvalues is 1, and the other one is -I, and the other is +I, and each occurs once. So we have here, so we have one, let's say, eigenvalue of 1, one eigenvalue of -I, and one eigenvalue of I. And if we go for the eigenvectors here, you'll get these complex eigenvectors as well.